Okay, now domain. Es obvio que domain is from 0 to infinity because the function que introduce restrictions es obvio que es infinity, es logarithmic. Logarithmic vale only x no, pero logarithmic yes. And the range, I suppose que is the same because the negative is not allowed here. And this is a square that is always positive, never negative. Okay, now ready to compute the y-intercept, the y-intercept. It's 0 times logarithm 0. Logarithm 0 is undefined. Undefined. Therefore, we have no. That's mean we have no y-intercept in this problem. No. X-intercept. F of x. In this case, no f. Sorry, it's m. The negative function. Okay, let me erase the letter. No f anymore. It's m. M of x equals 0. Then logarithm x times ln of x a squared equals 0. One solution is 0. Total out the domain. Another solution is logarithm of x equals 0, que es x equal 1. Yes, this is good. So we have one point, que es the point 1,0. It's our x-intercept. And we have no y-intercept. No. And one x-intercept. At the point 1,0. Okay. Okay. Well, maybe like asymptote, I believe, I suppose, is at x equals 0. I believe because logarithm have asymptote, vertical asymptote, and 0. But I will need to verification this. How do you verification? Easy. You compare the limit when the x approaches to 0 plus of our function. Plug in it. This is 0 times infinity. The logarithm 0 plus negative infinity, but negative infinity square positive infinity. This is indeterminate, not ready to apply L'Hopital. No, not ready. Now L'Hopital rule after L'Hopital rule. To copy limit when the x approaches to 0 plus of ln x square 1 over x. It's equivalent. Now when you plug in, logarithm of 0 is infinity or infinity. Because 1 over 0 is infinity. Infinity over infinity, ready to apply L'Hopital rule. Okay, L'Hopital rule now. L'Hopital rule now. Limit when the x approaches 0 plus, derivative logarithmic. Well, it's twice ln x times 1 over x. Chain rule. Derivative 1 over x is negative 1 over x squared. Well, you can do something. Okay. Plugging in. This is infinity over infinity. Whoosh. Infinity over infinity. We need to apply second time L'Hopital. Okay. But before that, I want to simplification a little bit. This is limited when the x approaches to 0 plus of 2 times ln x divided by negative 1 over x. Because we had simplification 1 of x on 1 of x. Okay. Now ready to apply L'Hopital rule. L'Hopital rule now is limited when the x approaches to 0 plus. Or the derivative logarithm is 2 over 1 over x divided by negative 1 over x squared again. The algebra is limited when the x approaches to 0 plus of bueno, this is minus 2x, no? Because the simplification here, let me see, 1 over x divided by negative 1 over x squared is negative x squared over x, no? X minus x. And don't forget that too. Now plug in es 0. And the answer is si es 0, no infinity positive or infinity negative. That means that we have no baric acid. The answer is no baric acid. The baric acid do not exist. Okay, now I want to determine the horizontal acid, or I don't know if we have or no, in behavior. So you compute the limit when the x approaches to positive infinity of x parenthesis natural by x squared. Plug in it. It's infinity times infinity squared. Wow, it's infinity, super infinity. It's infinity. And limited when it approaches to negative infinity have no sense. Remember that the domain is only positive value. Okay? So I can infer that my curve, I don't know exactly what's going on, but in the infinity, okay, the y go to infinity. So something like that. I don't know exactly what happened here, but it's in that direction. It's the end behavior. So actually, it's no horizontal acetone, no slant acetone. It's just end behavior. It's good to see the graph. Okay. Let's go to the calculus part. It's important. Okay, we compute the first derivative. Of course, you apply the product rule. Derivative x is 1 times ln x squared, no derivative. Plus derivative, this is 2 logarithm of x times 1 over x, get the derivative of the logarithm, multiplication by x. Wow, this is cancelled. So the first derivative expression is logarithm of x squared plus twice logarithm of x. Okay? If you want your factorization logarithm of x outside, we have logarithm of x plus 2 equal 0. So now 1 by 1 factor, logarithm of x equals 0, that means that x is equal 1. And the second is logarithm of x plus 2 equals 0, and logarithm of x equal minus 2. Therefore, x is equal e to the minus 2, que es 1 over e squared. Entonces we have two. We have two critical values, and I want to investigate in the first derivative test what happened in 1 and 1 over e. By the way, 1 over e is approximately e squared, sorry. It's approximately 0.135 in decimal. To have some idea where is that. We have 0 at the beginning of the domain. We have this number as 1 over e squared, que is approximately 0.135, and we investigate what? You take some testing points. Suppose I take here, I don't know, 0.1. You take here 0.5. And substitution, this and the first derivative expression. No, and also 2. Code 2 here. So after 2, suppose 2. So we have 2 partitions, 3 intervals, 3 testing points. Evaluate first derivative and 0.1. The answer is 0.69. Okay, positive. That means the function is increasing in this interval. F prime evaluate in 0.5 is negative 0.958, decreasing. And F prime evaluate in 2 is 1.86 increase. Now it's clear we have maximum here and minimum here, local, relative. This maximum and this minimum you evaluate in the original function f evaluate in 1 over e squared. The answer is approximately, is 0.54. Now this is that one is the maximum. The point is 0.135, 0.54 is the maximum. And evaluate in 1. 1 is easy, it's 0. 0 is 0, because logarithm 1 is 0. And the minimum is at the point 1,0. Okay, very well. Okay, now we compute the second derivative. Okay, second derivative is 2 natural logarithm of x times 1 over x plus 2 over x. 2 over x is a common factor, ln x plus 1. And force 0. Bueno, entonces the only solution is ln x plus 1 equals 0, ln x equals negative 1, therefore x is equal 1 over e. And this is the potential inflection point. Let me try. I apply now second derivative test. This is 1 over e. Okay, by the way, is 0.36 in decimal. They pick one value before and after. 1 and 1. This is 0.1, maybe, and this is 0.5. Arbitrary. I'm plugging in the second derivative at 0.1, and the answer is negative 26.05. See, it's negative. I don't care the value, I care the sign. It's concave down. And the second derivative, evaluating 0.5, is 1.227. It's concave up because it's positive. Now conclusion, this point is inflection point. Inflection point. Okay, by the way, the inflection point is located at the point. Okay, you evaluate in the inflection point, you evaluate the function in 1 over e in the origin, of course, and the answer is 1 over e. And the point is 1 over e, 1 over e is the inflection point. Let's see everything together and let's move. Now let's move. Okay, I copy the original function. I determine the minimum and maximum. Okay, this is the minimum. This is the minimum is 0. And 0, 0, 0, 0. 1,0. 1,0. Here, minimum max. Look, in green color. Inflection point in black color. Okay. Now the expression for the first derivative less than 0 decreasing part red color, and the same formula like inequality increasing is blue. Of course, we have nothing in the negative part. Remember, our domain starts at 0 to infinity. Okay, that is increasing, decreasing, and local max, local min. Now the second derivative. The second derivative increasing is concavely up, and second derivative negative is concavely down. Super. And the inflection point is double. Okay, 1 over e comma 1 over e. Excellent.